Hello everyone, my name is Juan Torres and today I'll present the parameterization of a 3D solid called a three-rectangular tetrahedron. I will also show how we can define a line and a surface inside this solid. First, let's introduce the figure. A three-rectangular tetrahedron is a tetrahedron where three edges meet at right angles at a single vertex, which in our case is the origin. You can think of it as the corner of a cube cut out by three coordinate planes. The distances a, b, and c lowercase represent the lengths of these edges from the origin to the vertices a, b, and c. Now, let's take a look at the parameterization. To describe all points inside the tetrahedron, we can use three parameters, r, s, and t, subject to the condition that the sum of these parameters is less or equal to 1, and each parameter is greater than 0. Otherwise, it would be outside the tetrahedron. However, this inequality makes it harder to generate grid points because R, S, and T cannot vary independently. For that reason, in our code, we use a reparameterization with three new variables, U, B, and W, each running independently from 0 to 1. In that way, we can use the MATLAB script plot parameterization to generate our plots. To reach the new parameterization, we analyze the three coordinate faces, which are the face OAB, OAC, and OBC, and construct formulas for x1, x2, and x3 in terms of u, b, and w, with u, b, and w all between 0 and 1. So u moves along the x1 axis, b spreads along the x2 depending on u, and w scales the height depending on both u and b. Now, let's implement it in MATLAB. In our case, we will analyze the case where the three distances a, b, and c are all equal to 1. So here, we first define these values. Then, we choose the number of divisions along each parameter so that we can generate the points. Next, we include the parameterization as I showed before. And after that, we define the grid for plotting the points inside the tetrahedron. Then define the surface of the tetrahedron, fixing one parameter and letting the other two vary. And finally, we define the edges of the tetrahedron varying only one parameter. The second part of this project aims to parameterize a line and a surface inside the solid that we defined in the first part. In this case, the line is defined from point C to the midpoint of AB. The parameterization of this line is straightforward. We use the formula for a line segment starting at C and ending at the midpoint M. Now, for the surface, we define the quadrilateral formed by point A, B, D, and E. Here, D is the midpoint of BC and E is the midpoint of AC, with two parameters S and T both between 0 and 1. By varying S and T, we generate the entire quadrilateral surface inside the tetrahedron. This is implemented in MATLAB, and we get the length of the curve and area of the surface. But before analyzing the numerical results from MATLAB, we should review what the exact theoretical values are. So for the length, we already know the coordinates of the points C and M. So we just use the formula of the distance and get a result of 1.22. Now, for the area, we also know the coordinates of the vertices A, B, E, and D, and we can define this area as the sum of the areas of two triangles, just like that. And we get a result of 0.6495. Returning now to the MATLAB values, we can see that the length of the curve doesn't change. This is because the curve is a straight line. On the other hand, the surface area does change. As the number of segments grows, the computed area converges to the exact value and the error is reduced. Here we can see a table with values for n equal to 10, 100, and 1000 segments. It shows clearly how the surface area approaches the exact value as n increases. Finally, this is a short demo showing that the code works. So here we have the code and I'm gonna run it. And here is our plot.